So good afternoon, everyone. First of all, I'd like to thank all the audience for being here to listen to what I have to tell you today. And also thank you to the organizers for giving me the opportunity to ramble on about my work. So what I'd like to talk to you about today is a problem that we have, one of the many problems that we have within our standard cosmological theory, the Lambda-CDM model. And to do that, I will be introducing, well, very briefly, the Lambda-CDM model, and then I will be telling you about the lensing anomaly, which is a problem that we have specifically about the CMB, which is not maybe as well known as the tensions that you've been hearing about yesterday and today, but it's a problem that is worth considering. And I will be telling you about 3 different pieces of work in which I try to reconsider the lensing anomaly and by reinterpreting it as either modified gravity or as a sign for massive, a non-zero, non-vanishing neutrino mass, and also finally by allowing the universe curvature parameter to vary freely. So what I'd like to tell you about the Lambda-CDM model is actually, I just want to tell you something about its components. I don't want to delve too deep into it. So as we know, what better way to do it than just like focusing on the name Lambda-CDM itself. For example, lambda is the cosmological, lambda is basically the cosmological constant, and it's when we take it to have a time dependence, we also dub it as dark energy, and it is an energy form that we need in order to explain what the universe is expanding, and it's doing so at an accelerated rate. Another important component is surely dark matter, which is very needed in order to explain why structures form and grow the way we observe them to. And finally also baryons, which is a less numerous component, but still very important to explain things that are very dear to us, like galaxies, stars like the sun, and human life, like ourselves. However, what we'll be focusing most about today are 2 other components, 2 other honorable mentions, as I call them. One of them is inflation, which is a very important addition to the standard theory, because this very rapid period of massive expansion of the universe is essential to explain what formed the initial anisotropies that then went on to form structures as we observe them today, and also radiation, which is negligible to the current dynamics of the universe, but it can also be used as a very important tool to test the standard theory. And I guess you already know what I mean by radiation, which is its main component, which is the cosmic microwave background. And as we can see from the picture, which is indeed in the background, we can see that we have hotter and colder spots, which means that we can observe photons that are hotter and colder in different points in the sky, and we can use this spatial difference of the temperature of these photons to actually do cosmology, to do physics. And the way we do it is by transforming these anisotropies into a so-called power spectrum. Okay, in this power spectrum, we have these oscillations, these peaks and troughs, which can tell us plenty about many things within the standard theory. As we can see, like what we measure, which are these orange and blue points that are taken from Planck data and ACT, which span a pretty large range of multiples. These points have been measured to be very precise, in a very precise way. And it is so precise that some of the error bars cannot be seen. And as we see, the Lambda-CDM prediction, which is the continuous line, is actually a very good fit. And CMB, this is the reason why I see the CMB is often dubbed as one of the main proofs that the Lambda-CDM is indeed a very strong model for the dynamics of the universe. And the reason why I said that we can do cosmology with it is because indeed the spectrum is very sensitive to different parameters that are making up the model. To baryons, for example, as we see down here. And as we see, if we increase the amount of baryons that are in the universe, then we see, for example, that the first peak tends to be enhanced, while the second one tends to be suppressed. And in fact, the ratio between these 2 peaks is what is directly sensitive to the quantity of baryons. Also, the quantity of dark matter is something that instead tends to suppress the spectrum. So by varying the spectrum and comparing it to the data, we are able to constrain all these parameters to very high precision. And in fact, as I showed you before, like this error bar, the error bars that we measure actually do not leave much leeway for these parameters to change that much. And that is why most of the lambda CDM6 parameters are constrained within the lambda CDM model to sub% precision. And it is indeed the most important one of the most important problems that we have to test the universe. However, even though the CMB, as I told you, is an indicator, is indicating to us that the lambda CDM model is indeed a very good model for the universe, there are also problems. As you know, there are tensions that we measured when we're measuring the H naught from the CMB, but there are also like maybe lesser known or like somewhat like less relevant tensions, but just because there are like less standard deviations away from the standard theory, like for example the lensing anomaly. The lensing anomaly is a tension that is like purely defined within the scope of the CMB. And to understand it, we need to introduce the so-called lensing parameter here, which is just a rescaling of the CMB spectrum that we can see here. And it's a way to measure how much more lensing the CMB photons can be measured to have compared to the standard theory. So the effect of lensing, as you can see from this picture, is that of smoothing the peaks out. As we can see, all of these acoustic peaks are basically like getting flatter, and the power that is getting lost at low to medium multiples is actually regained at higher multiples. So there is also a shift in power to an extent. And this is also, again, an effect that we can measure. And what happened is that in the 2018 data release, Planck seemed to measure a value of the lensing parameter, which should be 1 by definition, in lambda CDM, but also in any other parameter. In any other model. In any model, we expect to see the amount of lensing that the model predicts, not more, not less. However, what Planck saw is that within the standard theory, as we can see from the black contour here, there seems to be evidence for a stronger lensing that we could actually predict from the standard lambda CDM model. And there are a couple of ways in which we can try to solve this anomaly. And one is by considering different likelihoods, the different likelihoods that have been developed for like high multiples data in Planck. Like Planck is the official one, but then we also have CamSpec here, or helipop. And as we can see from the contours, the blue for helipop and the red one for, the blue one for CamSpec and the red one for helipop, we are moving more and more towards the expectation for the lensing anomaly within the standard model, which is AL equal to 1. Another way to interpret this weird result is by looking at scenarios that are beyond the standard theory, and that's what I did along with other collaborators, including Eleonora herself at the University of Sheffield, by looking at different extensions of the model. And one that I'd like to start with is modified gravity. And the way that we faced this problem, or this question that we wanted to ask, was by considering two different modifications of the standard theory. So one is also called the mu-sigma parametrization, and it's consists in introducing two parameters that are introduce in their own time modifications to the Poisson equation, as we can see here, the mu parameter, and also most importantly to my talk, there is also modification to the lensing equation. This is called lensing equations because the sum of the two perturbation potentials is directly sensitive to lensing, and this equation is linking this the amount of lensing that also CMB photons experience to to delta m, which is the perturbation of which describes matter perturbations. So there is a direct link between obviously lensing and the way structures grow, and we can modify the standard picture by introducing these two different parameters. A different way of doing it is by introducing a parameter called gamma, which is in this case changing the matter perturbation directly by acting essentially on what we do here. We just assume an ansatz for delta m, and the idea of this parameterization is that while most modified gravity theories tend to predict the same expansion history, which can be codified by omega meta, they also at the same time tend to have a different growth of structure, which is codified by delta m, and so this difference has to be we should be able to see this difference between by looking at the gamma parameter, which within the standard theory should take the value of 0.55, and similarly the mu and sigma parameters should be 0 within the standard theory. And modified gravity, just one last note, is actually having a very, very similar effect, as you can see from the spectrum here, as the lensing anomaly. We can also see a smoothing of the peaks, and so we expect the two things to be very similar. So we wonder if, like the solution of the lensing anomaly could also be linked to the solution to the apparent evidence for modified gravity that also Planck 2018 data seem to show. From the red contour here, we're slightly more than 2 standard deviations away from the vertical line, which represents, again, the standard theory, GR. And so with it, we looked at, again, different likelihoods, which I introduced before, like, well, Plick, the main one, and then also CamSpec and Helipop. And very similarly to the lensing parameter, we see that there is a shift. There is a shift towards the standard theory. We go from the red contour, which is, again, Plick, and then the green one, which is CamSpec, and then Helipop. And by the time we get to Helipop, we get like full consistency with the standard theory within 2 standard deviations. So changing likelihoods can help, and at the same time, we are basically recasting this lensing anomaly from a lensing anomaly to a slight evidence for modified gravity. So this is not to say that we are finding modified gravity, but just to say that the two effects are indeed like correlated to each other. But at the same time, by considering different likelihoods of within the CMB data, we can bring both of those parameters, so both A lens and the modified gravity parameter sigma, they can both be shown to be consistent with general relativity, which is represented essentially by the point where these two lines are crossing. Okay. So now another way to reinterpret the lensing anomaly is by looking actually at another way of influencing or changing the way structures are growing in the universe, which is by introducing massive neutrinos. So the effect of massive neutrinos that have a non-zero mass is that of actually suppressing matter growth, and this suppression is also translated into a suppression of the CMB power spectrum itself. As we can see from the image, there is both a suppression and also a slight shift towards kind of lower multiples. But again, just like in the case of the lensing parameter and in the case of the sigma parameter for modified gravity, the total neutrino mass is a parameter that can have an important effect on the spectrum, and we can use it to test whether this can be seen from the data or it cannot. So the reason why that prompted us to look at the neutrino mass, the total neutrino mass, was essentially just the fact that the new Daisy constraints, which we see, the Daisy constraints on this parameter, the neutrino mass, which we found in a paper that is now in preparation and should be coming out by the end of this week, is actually very, very tight, and it's excluding like the value that has been found both by neutrino oscillation experiments, both for the inverted ordering and the normal ordering. So these are two possibilities that these are two possible total masses that the neutrinos can take, because and the reason why we only have an upper limit is because we still cannot resolve the single neutrino masses, but instead we can have a lower bound. And as we can see, again, the Daisy data are actually excluding both at 99% certainty. So this is a very tight constraint, and you might wonder why. We could even take it at face value. So why would we want to relax this constraint on the neutrino mass? Well, the idea is essentially that, as it's been shown in some works, even within the standard theory, if we somehow allow for neutrino masses to also take negative values, Daisy data actually seem to show that the neutrino mass could even take, on average, a negative value, which is obviously unphysical. It doesn't really make any sense. However, by introducing dark energy models like WNOWA, the CPL parametrization, or even mirage dark energy, which is just like W naught WA, but we're just enforcing a specific relationship between these two parameters. If we introduce these two modifications, then we're actually able to bring the neutrino mass to be, we're able to relax this constraint and to be fairly consistent with the inverted ordering, but also at the same time with the normal ordering. So we decided to see if a modification not in dark energy, but a modification in the form of dark energy, but a modification in the form of modified gravity could actually relax this problem, well, this very tight constraint. And so we did by looking at the gamma parameterization that I mentioned before, this parameter here, which I remind you should be taking a value of around 0.55 within the standard theory. And what we found is that there is some alleviation. For example, as we can see here, we are basically recovering in all of these cases. We are recovering the normal ordering, but not in all cases we can recover the inverted ordering. But all of these constraints, as you can see, are still pretty tight. And at the same time, the gamma parameter is actually tending to values that are inconsistent with lambda CDM, and so we can effectively say that modified gravity does not seem to be enough to be relieving the very strong constraint that we were able to put on neutrinos. The situation is improving, but maybe not so much. And in fact, we can see that there is some correlation from the plot here, but not too strong. So modified gravity is probably not the best solution to relax the neutrino bound. So finally, I was done. The final idea that we wanted to test was looking at a model where the universe can be assumed to be closed, can be taken to be closed. So what we did was taking a primordial spectrum where that has a little correction codified by the phi function here, which depends on k, the curvature. And the point of this correction is to suppress the power of the primordial power spectrum at very large scales, as we can see from the picture here. So now this is something that is done by the Planck collaboration, and this is like essentially the type of modification that they used when they showed that there was a slight evidence for omega k to be different from zero, the curvature to be different from zero, which we see here from the red contour. However, this is a phenomenological model that is not really justified by any theory in particular. So what we did was taking a model that is actually justified theoretically by a quantum gravity model, which also contains a correcting factor, which is different from this factor here, which is however very long and cumbersome. So I might show it to you later if you're interested. So we tried to see if we could still detect a non-zero curvature, even in this case. And what we found is that actually the evidence for curvature is decreasing a lot by considering a model that is actually underpinned by an actual theory. So we see that the omega k, again, curvature, which should be zero within the standard theory, is actually getting closer and closer to getting closer and closer to zero. Here we have just like a 2 sigma evidence, but as we change and go towards change likelihoods, like we did for the lensing anomaly, like we did for modified gravity, the evidence is getting less and less strong until we get to the case with CamSpec and lensing together, which are essentially consistent with zero at less than 2 standard deviations. And this is also the representation that we can see in 1D contours. And finally, this is, again, not surprising. We change likelihoods. We are getting closer to the standard value. And that is simply because, again, just like the lensing anomaly, omega k also has a very similar effect on the lensing spectrum. And so as we change likelihoods, we can essentially resolve both. So these are my conclusions, but I think I've taken a lot of your time already. So I think I'll just thank you and take questions if you have any.
Thank you so much for the nice talk. Questions? Yes, Eric?
Thank you, very, very nice. For the modified gravity, sigma and mu parts, those are generally time dependent. Have you looked at different, how your constraints change as you look at different time dependencies?
Yeah, so no, we haven't looked at time dependencies, but yeah, I'm aware that you can take a time and also scale dependence. But in this case, our purpose was purely that of detecting any deviation at all from the data, so we didn't assume any specific time dependence.
Yeah, one of the issues is that if you take the time dependence to be, for example, proportional to cosmological constant density,
yeah, like dark energy,
then it really weakens, because it goes as a cubed at high redshift, it completely weakens the CMB constraints.
Oh, okay.
And that if you took a different time dependence, the weighting, that might weight the CMB more, and you might get tighter constraints or shifted constraints, for example.
Yeah, yeah, that's definitely a venue.
So that's why it's nice to look at a few different time dependences and see how robust the conclusions are.
Sure. Yeah, that could be surely an interesting extension. Thank you.
Thank you. Any other questions? Hanyu, here.
Hi, very nice talk. And can you change the page to the how DLTT evolve with the variation of AL?
Yes.
Yeah.
This,
yeah,
right?
This one, yeah. And I see the formula gives DLTT is equal to AL DLTT. Looks like this DLTT will overall change with the value of AL, but in the plot, I think it's it doesn't choose this overall change with you when you change the value of AL for the DLTT.
Oh, so. As in, you mean, so sorry, could you repeat the question?
Yeah, my question is, as the formulas tells, it should be changed overall, like it's a lift overall DLTT.
Yeah, so I would say, I have to admit, like, this formula is like, say, half a lie, because actually the lensing parameter is acting really on the lensing spectrum, rather than directly on the overall spectrum itself. So we have basically. We have an enhancement, so let's say kind of a shift in the lensing spectrum, but then the lensing spectrum is convolved with the primary anisotropies, and that's what ends up giving you this shape. So it is a little, this is like slightly inaccurate, but this just to give you an idea of how the lensing parameter is acting. So does that answer your question?
Yeah, we can discuss it more later.
Sure.
Yeah.
Thank you for the question.
Thank you.
Thank you for a very nice talk. So my question is regarding the neutrino constraints on the mass. So it seems like, naively, that lambda CDM excludes a positive neutrino mass.
Yeah,
or at least,
like it, yeah.
I mean, so if you just...
So in this picture, you mean?
Yeah, in that picture. So if you just put in a prior, putting in the particle physics experiment constraints, would that mean that it would increase significantly the preference of dynamical dark energy from 3 sigma to even more?
It's likely to happen, I think, because we actually did that, and that's actually a part that I think I forgot to say in the results. So we also, in the second and the fourth case, we actually enforced in the priors to the neutrino oscillation experiments lower bound, which is 0.06 electron volts for normal ordering, and we do get an improvement. We do get an improvement in both cases in the constraint in the neutrino mass. So yeah, because because the constraint is getting relaxed, then this evidence has to, I guess, might end up into evidence for into stronger evidence for dynamical dark energy, because I guess modified gravity couldn't really absorb it that much. So maybe in part, if we chose a dynamical dark energy, it could be we could have a stronger evidence for dynamical dark energy. I think so. Yeah.
Thank you.
Thanks.
Any other questions? No, so let's thank Enrico again.